Okay, let's see another problem on VLIW. So this is the question now. In the question they have given this program, and we have to schedule it in the VLIW processor with the bundle of two memory reference, one floating point operation, one integer operation every clock cycle. So we have the same bundle as the previous problem, and here the specialty is they didn't give number of times you have to unroll the loop. So we have to figure it out how many times you have to unroll loops in such a way that there is no stalls and the same latencies they have given. So first what we will do, we will write the what are the destination registers of each and every instruction. So first LD. So for LD, okay, for LD it is F0, and for add D it is F4, and F0 is from LD and F2 is fixed here, so we have to make sure not to use F2. And then we have SD from F4, which is here. So these are the only instructions they are using. So now we have to try to unroll the loop. So for the first time what we will do, we just copy it from the question. So we will write the first unrolling. First unrolling will come as LD F0, 0 of R1, add D F4, F0, F2, SD 0 of R1, F4, and dat IU R1, now we don't know how we cannot write the fix-up code. The dat IU and BNE are the fix-up code, so we should not write them as part of the first iteration. So this is a loop fix-up code. So we are not going to bother about this loop fix-up code. We are going to have it at the last. So we will put dat IU here. Dat IU R1, R1, and we are going to decrement each and every time by -8. Previous question it was positive. Here we are going backwards. So a negative R8. But in stack point of view, or going forward. Okay, so this is the loop fix-up code, and the loop will come here. So now we don't know how many times you have to unroll. So for the first time, we will just blindly fill this this particular unroll into our VLIW slots, so that we can figure it out how many times you have to unroll by looking at how many slots they are not filled. So the first time we will fill the slots now. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, so the first unroll, we will put the memory reference LD F0, 0 of R1. Okay, and the add IU has to be, and we have to know where we have to place the add IU, because we didn't note down the stalls. So let's figure out the stalls also in the question. If you see in the question, FP to FP is 3 stalls, FP to SD. So FP to SD, the rest add to store will have 2 stalls, and LD to add will have 1 stall. These two only are as part of our given program. So we will remember FP to SD and LD to FP. These are first two will have 1 stall, and the second and third will have the 2 stalls. So we will remember that, and we will fill the slots accordingly. Okay, so the first slot we have to fill it now. Okay, the first slot LD F0, 0 of R1, and we'll have one delay and we have to put the add F4 comma F0 comma F2. Then we'll have two delays and put the store SD 0 of R1 comma F4. So this is the slot. Now you will see whether we can accommodate within this enrollment also, because obviously we cannot, but we'll see whether how many slots are getting not getting filled. So if you put DADIU here, branch has to go on somewhere here only, because we cannot execute branch prior to our store. So branch has to come here, and DADIU can go up in 1, 2, 3 ways. But if you put DADIU here, means you will have two stalls here. So at least another one time you have to unroll the loop so that we can fill those two slots. So let's unroll the loop once again. So LD F. Now we are going to increment by 10. Say for example you are incrementing by 10, because that's the usual way we are doing. So increment by 10, adding 10, and we have displacement is -8, so you will have to adjust it by -8 R1, and then add the F14 comma F10 comma F2 SD of 0 -8 -8 of R1 comma F14. We'll try to schedule these three now. So if you put already load is not dependent on all these things, so we will try to fill it here. So let's fill it here now. Now this add has to be 1 clock cycle away from this load, so obviously we cannot fill it here. We try to fill it here, but already there exists another add, so we can fill it in the next slot only. So add the F14 comma F10 comma F2. Now this from these instruction, 2 clock cycle away the store has to be there, so you will put the store here is store of -8 of R1 comma F14. Now let's try to fill the DADIU fix-up code and the branch not equal. So branch not equal will come here, and DADIU can go here, but still one slot will be stalled. So we try to unroll it again once, but that is but we could have stopped with this unrolling if we made a smarter move of putting this load is here. Say for example, instead of putting that load up there, if I put that load up here, okay, say for example if I put my this load up here, down in the second clock cycle, here or here somewhere in this place instead of this place, still my load is 1 clock cycle away from this add. Sorry, my add is 1 clock cycle away from this load, and this add is 2 clock cycle away, before the store. Now load is we have eliminated this one, so now we can fill the DAD here and branch not equal here. Correct. So now we have filled all the slots with only this many within the second unroll of the same program itself within. Now we don't need to unroll it for another time. So it is just a trial and error strategy. That's why I said to in the first problem itself, I said to write it in pencil so that we can modify it easily. So now we will just erase my load from this point, and I will put my DADI instruction here. So all this I will erase it here. So I will put the loop fix-up code. First loop fix-up code is DADIU here. So now I have unrolled it twice. So for unrolling it once, we change it to -8. So for unrolling twice, we will be changing -8 and another -8. So -16 we have to put DADIU of -16. But since DADIU is so now we have another problem. So DADIU has to be after the store, but we are moving the DADIU before the store. So again we have to change our store and the displacement of the store. We'll see how to change that one also. R1 comma minus 16. So my, say for example, my R1 contain 2016. So the first store should have stored in 2016, and the second store should have stored in 2018, and my R2 should have been pointing to 2016. This is what had we done. But what we did, before itself we made our point, 2000 here. So before itself we made our R2 to point here. So obviously storing, it's like saying that you are storing it 2000, but we have to store in 2016. So we have to change this value to 16. Now the displacement will be, instead of 0 it will be 16, and from this 2008. So this displacement you have to change it to plus 8. This displacement we have to change it to plus 8. So now according to my data view, my store is also fixed its displacement. Now I can fill in my branch instruction at the last slot here. So BNE R1 comma R2 comma loop. So now all the slots have been filled with no stalls within 2 unrolling itself, and it took me 7 clock cycles. So that is the solution for this VLIW problem. Now say for example in the question they have given it to unroll it for a four times. So what you will do, as usual, you will move this load to there and put another 2 loads here, and you fill the 2 adds here, which will make this 2 stores to come here, and automatically you can fill the data U and the BNE here. So it will come to 9 clock cycles. So it's up like once you got the hang of it, you can extend this problem easily within few minutes.